All right, a couple of final things I want to talk about in this section. The first is just a little bit of jargon, and it gets used a little bit in the course, so we'll talk about it. If you have a conditional statement, if P then Q, there's some related statements that that come up. The converse and the contrapositive, in some sense, are the most important. They're the ones that come up the most. But there's only one more, and that's the inverse. We might as well see them all. So the converse, what that means is just the if part becomes the then part, and the then part becomes the if part. So they get flipped. The inverse has the negation of the if and then part. So you just reverse the truth values of P and Q. And then the contrapositive is both combined. You flip and you reverse. So I'll let you guys try this. Here is an if-then statement. If C is a cat, then C meows. So pause the video and see if you guys can write down the converse, inverse, and contrapositive of this statement. All right, so the converse just flips the if and then part. So the then part is now the if part. So if C meows, then C is a cat. That's the converse. The second one is the inverse. So we just reverse the truth value. So if C is not a cat, then C does not meow. And finally, the contrapositive does both. So we're going to flip and reverse. So if C does not meow, then C is not a cat. So there are the converse, inverse, and contrapositive. And I want to make a quick note. And this is very important. One of these is logically equivalent to the original, and that one is indeed the contrapositive. So the contrapositive and the original statement are logically equivalent. Remember, that means they mean the same thing logically. So you can replace one with the other. And I'll leave it as a little exercise for you guys. We know that the truth table, let me do a little truth table here. We know the truth table for if P then Q. See if you can come up with a truth table for if not Q, then not P. What you'll also need a truth table for the negation of P, the negation of Q. They're easy. Let me just do P for you. True, true, false, false would become false, false, true, true, for example. And what you'll find is that the original statement and, I'll put brackets around this so it's a little easier to read, and the the contrapositive have the exact same truth values. So try and work that out if you can. The last thing I want to talk about are biconditional statements. And that's just shorthand for kind of two conditional statements put together with an and. So you have if P then Q, and its converse, if Q then P. And the combining words that you'll see to mean a biconditional, you'll either see if and only if. Mathematicians like to use this if with two F's. It doesn't come up too much outside of university math, but you might see it. And the one that I use the most is exactly when. So they mean a biconditional. So before I show an example of one written out, I just want to talk about what it means. So let's look at this examples 1 and 2. These are just conditional statements. So if a number is even, then it ends in 2, 4, 6, 8, or 0. And this is something that we'll prove a little bit later on in the course. We also have the converse statement, where we flip the if and then parts. If a number ends in 2, 4, 6, 8, or 0, then it is even. So we know all even numbers end in 2, 4, 6, 8, or 0. So this is a true if-then statement. And if a number ends in 2, 4, 6, 8, or 0, then it is even. That is also true. Now I want to draw these in terms of all statements. So rewording 1 says all even numbers end in 2, 4, 6, 8, or 0. So here are our even numbers. Here are numbers ending in 2, 4, 6, 8, or 0. So that's what statement 1 is saying. And it's true. Statement 2 is saying the converse. If a number ends in 2, 4, 6, 8, or 0, then it is even. So this is saying if it ends in 2, 4, 6, 8, or 0, if the ones digit is 2, 4, 6, 8, or 0, then the number is even. All numbers that end in 2, 4, 6, 8, or 0 are even. We know both of these are true, so both diagrams have to be correct. But look at this. In diagram 1, you have even on the inside and ending in 2, 4, 6, 8, or 0 on the outside, and 2, you have the reverse. So how can both be true? And if you think about it, the only way that these are true at the same time is if they're both the same fence. So if they're right next to each other, if there's no space in between them. In fact, let me make this fence red so it's a little bit easier to see. So the even fence will be red. So the only way this is true is if both fences are literally the same fence. So both fences are the same. They're right on top of each other. That's the only way that both of these diagrams can be true. Okay. So what does that mean? That means the only numbers inside the fence are ones that are even and end in 2, 4, 6, 8, or 0. And on the outside is everything else. If you think about it, on the outside of both diagrams are things that aren't even and don't end in 2, 4, 6, 8, or 0. So not even and do not end in 2, 4, 6, 8, 0. What's nice about these biconditionals is basically it says the two concepts are the same. Being even is the same as ending in 2, 4, 6, 8, or 0. And that's not always the case. So There are situations, of course, where the original statement is true and the converse is not, or the other way around. Here's an example of one where it's not, where the converse isn't true. So we know that if a number ends in 2, then it is even. That's true. 2, 12, 22, 32, 42, whatever. They're all even numbers. But what's the converse? The converse is if a number is even, then it ends in a 2. And we know that's not true. We can come up with a counterexample. So this, while the first one was true, the converse is not true. So that means that we can find a counterexample for this. And our counterexample, how about 4? 4 is an even number. 4 is 2 times 2. But 4 does not end in a 2. It ends in a 4. So there is our counterexample. Or you could use pretty much any even number that doesn't end in 2. And we're good to go. So, biconditionals are true exactly when P and Q have the same truth value. If we look at our diagram here, there's only 2 regions. The region inside of the fence has P true and Q true. The region outside the fence has P false, that's not even, and Q false, does not end in 2, 4, 6, 8, or 0. So there's only 2 regions, and the regions are when the biconditional is true. So either P and Q are both true, or P and Q are both false. And that basically means that one stands in for the other. It's the same concept, worded a little differently.